Arduino is a great option for developing an early prototype of a new product, but they're not at all appropriate when it comes to mass production. So in this video, I'm going to show you how to design your own custom Arduino Uno board, which you can then use in a mass manufactured commercial product. Unlike many other shorter videos on PCB design, which are heavily edited, this video is mostly in real time as I design the custom Arduino Uno board using the free open source KiCad PCB design software. Although I'm using KiCad for this tutorial, the focus is not on the software used, but instead on the fundamental engineering that is required to design your own custom PCB. Also in the description below, there's a link so you can download all of the design files used in this tutorial. Hi, I'm John Teal with Predictable Designs. Let's get started. So here you can see the full schematic for the Arduino Uno. Rev 3 is the one that we're going to be doing. So I'm going to do a quick review on just sort of the main components in this schematic. Then we'll start designing this schematic in the KiCad software. And while doing that, then I'll go into a lot greater detail on every single component and what the purpose of that component is. Okay, so we have the two main blocks here. Just zoom in a bit. So we have, this is an AT Mega microcontroller, and this is another AT Mega microcontroller. So surprisingly, the Uno actually has two separate microcontrollers, and they're both AT Mega. Now, this is never honestly a strategy that I would recommend for designing a board to have two separate microcontrollers. But for some reason, I don't know if they perhaps, got some kind of discount on certain parts early on, but the microcontrollers that were selected for the Uno are in most cases not the way I would select to do a full custom product today. However, for this tutorial, I want to follow exactly the Uno schematic as much as possible. But while going through that schematic, I'm still going to review with you and share with you what I think maybe would be better choices or better design solutions versus what they have chosen. So they actually have this first microcontroller, AT Mega. It has only one purpose, and that purpose is to serve as a USB to UART converter. Because you program the Arduino through the Arduino IDE, which connects directly to a USB port on the board that you're programming. However, the primary microcontroller, which is this one here, this is the one that you'll actually, your sketches and everything run on. This AT Mega 328P does not have any USB support. So there's no USB port on here. So it would be impossible to program this through a USB interface without having a special converter that converts between USB to what's called UART. And UART is just basically a simple serial protocol that any microcontroller supports. USB is quite a bit different. So this basically just takes the USB, converts it to a UART or just a serial protocol, and then that gets passed on to the primary microcontroller. Now, part of the reason, your first question may be, well, if this microcontroller has the USB, then why not just use this microcontroller to run the sketch? Well, the AT Mega 16U2, which is this one, is very limited on resources. I mean, all of these are 8-bit microcontrollers, so they're all relatively limited in resources, but the AT Mega 16U is even more limited. It only has 16 kilobytes of program space, and it only has 512 bytes of RAM, so it's very limited. Versus the AT Mega, I'm not going to say it's, it has lots of resources, but at least it does have 32 kilobytes of program space and 2 kilobytes of RAM storage space. So it's got quite a bit more memory. It's got more I/O than this AT Mega. So for whatever reason, the designers at Arduino decided, well, let's use this AT Mega because we like its memory that it comes with. But the AT Mega, let's go ahead and just use that for our USB conversion. Well, I mean, in theory, it's okay, but you're doubling the complexity. Now you've got two microcontrollers you have to program. You've got two microcontroller chips you have to pay for, and you've got two of lots of other things. You've got two crystals. This has a 16 megahertz crystal, and this has a 16 megahertz crystal. They both have their own programming port here. So it makes a lot of duplication, and it's very inefficient to do it this way. And honestly, I don't think I've ever seen this, almost rarely ever done on a commercial product. This is kind of a Arduino Uno specific. Now, other Arduino boards that still use AT Mega 8-bit microcontrollers like the Leonardo, they have basically eliminated this two microcontroller issue, and instead they've gone with the AT Mega 32U4, which is in this same family. So it includes a built-in USB port, but it has more memory, so it eliminates the need for the second microcontroller. However, it's a pricey microcontroller. All of these tend to be on the pricey side for what you get, considering that these AT Mega microcontrollers are literally using, pretty much technology from the 1970s. 8-bit microcontrollers have been around. I mean, I've been programming 8-bit microprocessors since I was just a young child. So they've been around for quite a while, and they're expensive. Now, you can get much higher performance microcontrollers with much better resources, more memory, even more I/O, much higher clock speeds, native USB, and you can get it cheaper than AT Mega. So just something to keep in mind when you are designing your commercial product. But once again, for this tutorial, my main focus is going to be on teaching you how to make an Arduino Uno board that's almost exactly like the Arduino Uno. But along the ways, I'm going to sort of be sharing little tips here and there on things that you may want to consider if this is a product that you're going to bring to market. Okay, so we have this microcontroller we talked about. We have this is the main microcontroller. You have all the support circuitry here. This microcontroller has its various support circuitry. You have the USB port that comes in. It does two things. It provides power, so it provides a 5-volt signal, and then it also has two data lines that tie into this microcontroller for the communication. And then, of course, there's a ground connection. Then up at the top, what we have here a linear regulator. So this takes a 5-volt DC and converts it down to 3.3-volt DC. And really, this 3.3 doesn't really power anything. Everything on the board is powered by 5 volts, but this is then brought to an output header, so you could use it for other applications, or if you had to power something externally with 3.3 volts, then you could use this regulator with limitations, which I'll discuss as we get closer. That 3.3 volt is actually also used here, and what this is it's really an op amp, but it's operating like a comparator. And this is basically, I'll go over this in detail, but this circuit's just kind of looking to see if you've got a separate input power supply. Then it will flip a switch and choose one of the power sources. Then this other op amp is connected up and is basically serving as a buffer, just to drive an LED. Once again, I'll go over that in more detail. Then we have, this is your main DC power input. So you can power this through the USB, which provides 5 volts, or you can power the board directly through its power supply input. And that can go up from 6 volts to 20 volts. And then that feeds over into this other linear regulator, which outputs 5 volts, which is then what powers everything else. And that's pretty much it. The other stuff you see here is either, just LEDs for various purposes. This is just a header. These are the various output headers where you can, connect shields and things to the board. We have our two programming connectors, and then we just have all the various support circuitry, capacitors, resistors, inductors, and such, and I'll go over those in detail once we start designing the circuit in KiCad. Now don't forget, in the description below there's a link so you can download all of the design files used in this tutorial. Okay, so that is everything in the schematic. Now let's go ahead and jump over into KiCad. So this is our schematic that we are starting in the KiCad software. And I want to emphasize that the focus of this tutorial is about the fundamentals of designing the printed circuit board and the schematic and the Arduino environment, and not specifically using KiCad software. You can use any PCB design software that you're comfortable using. I just, in the past, I've always liked dip trace a lot, but I've kind of switched to KiCad recently, mainly due to the fact that it's free and it's the easiest for anyone to access, since even the full version is free, since it's open source. So what I've done here is I've gone ahead and kind of placed all the most of the components that we're going to need, just because I don't want to be spending time, searching through the library and trying to find the various components. Some of these were not, most of these were in the default library, but occasionally you'll have to create, either you can find a symbol online for a component and you can import that, or you can create your own symbol. But these are most of the components that we're going to be using. So I'm going to switch back to our schematic here, and we're going to focus on, we'll kind of just start with how the data flows. So data comes into the USB, and then so we're going to cover this first microcontroller that serves as the USB to UART converter. Then I'll switch over and we'll work on this part of the schematic for the primary microcontroller, and then we'll jump up here and do this comparator, buffer, and the various voltage regulators, and any of the headers that you want to do also. Okay, so this is the part of the circuit. Let me just zoom in here on what we're going to be focusing on. And we kind of have, so let me do just a quick review of everything in this circuit. We have, this is our native programming connector. So programming in Arduino, you normally program it through the Arduino IDE. Or not through the, well, when programming it through the Arduino IDE, you use just a USB interface. However, when developing your own board, you can do that eventually, but you can't program it the first time through the USB. So for instance, this one here that connects to the USB, unfortunately, you can't just connect the Arduino IDE to your computer through this USB and start programming it, because this microcontroller is missing what's called a USB bootloader. So it doesn't know how to load firmware its embedded firmware through the USB port. You have to program it to tell it how to do that. Well, it's kind of the catch-22. You can't program it through the USB port to tell it how to program through the USB port. So that means at least the first time, and if you're not using Arduino IDE specifically, then you'll do this every time, but you'll program it through the special port that requires a special external device called a debugger. You'll see it called in-circuit serial programmer, in-circuit serial debugger. There's lots of names for it, but it's basically just a piece of hardware that allows you to convert from USB on your computer to the serial programming protocol used for that specific microcontroller. Now, different microcontrollers have different standards for programming them, so the programmer needed will typically be unique for the microcontroller, or at least that family of microcontroller. So we have our native programming port, and it's mainly, you've got like a reset signal, a clock, and you've got two data lines. One is MISO is master in, slave out, and MOSI is master out, slave in. So these are just the two unidirectional data lines that it's part of an interface called SPI. And that's what we're going to be using to program the ATmega natively, the first time at least. Then we have some other. Let's follow here. We have the USB port. So the power comes in. This is 5 volts. Comes in 5-volt DC. We're going to pass it through F1, which is just it's called a PTC Fuse. It's positive temperature coefficient. It's what the PTC stands for. It basically is just it's a varistor that when it gets hot, so it's got a positive temperature coefficient, so its resistance increases as the temperature increases. So what happens is when it starts to get so much current through this fuse, it starts to heat up. Well, then the resistance just climbs so much that it limits the current. So this basically acts as a fuse. It's a resettable fuse. All you have to do is take away power, let the resistor cool back down, and then it basically resets. So this is called a resettable PTC fuse. And that's the purpose here is, like any fuse, is to limit how much current can flow. So this is on the power line coming from the USB port, comes through this fuse, and then they labeled it USB VCC, which is what we'll take that off of. Then we've got our 2 USB data lines. They have some just a small series resistor, like 22 ohms. This is typically for ESD protection, secondary ESD protection. It's just going to limit how much current can flow through these lines. If there was like a short circuit, for instance, or if there was a voltage spike and you've got current flowing into these pins, then these will limit it. But then we also have these 2 devices here, Z1 and Z2, which they limit they are for ESD protection of the data lines. And I'll pull up the data sheet and show you the details on those in a moment. Then we have L1 is a ferrite bead, and this bead is just to stop like high frequency noise injection. Then we just have some decoupling capacitors on our VCC. This is just to hold the supply at to hold it steady. So this capacitor stores some charge to hold the supply stable. Then we have, this is our crystal with the 2 shunt capacitors that go with it. These are 2 capacitors that are required to go with the 16 megahertz crystal. So this is the master timing clock for the microcontroller. Everything in a microcontroller, microprocessor, in the world of digital, almost always there's a clock that everything synchronizes to this clock. The faster this clock, then the faster data is typically processed by that microcontroller. This is only 16 megahertz, which is pretty lower end for even a microcontroller. For microprocessors, like in your phone or your computer, this would be 2, 3, 4 gigahertz, so 1,000 megahertz. So much faster than only 16 megahertz. But this is not a microprocessor or microcontroller even that you would ever use for processing lots of data, just because it is relatively slow and it's only 8-bit versus most other more modern microcontrollers are going to be 32-bit, and then microprocessors are 64 bits or more. Okay, then we have, let's see what else we have. That's kind of there's a couple LEDs connected here that we can turn these LEDs on. Basically, if either of these lines, they're calling it transmit and receive. So we can see when we're transmitting data or receiving data by these blinking. What happens is this power supply goes through the resistor, through the LED, but no current flows unless this I/O pin is brought low to ground, and then current flows through from 5 volts through the diode to ground, and the LED turns on. When this goes high, then there's no current flow because this is 5 volts, this is 5 volts, and there's no voltage difference. So there's no current flowing, and the LEDs are turned off. Let's see here. These are just some various, it looks like just a little another little header here for bringing out some of the pins, some of the I/O pins. And since the emphasis of this tutorial, even though we're emulating the Arduino Uno, the design here, the purpose is so you can design your own custom Arduino replacement, which means you'll want to get away from doing things like shields and such. So I'm probably not going to follow, the footprint exactly for this board to match it with the Arduino Uno, because the purpose isn't really for you to design just a copy of an Arduino Uno that you can use shields and things with. The purpose is for you to understand how to design a custom microcontroller board, and then any of the functions that are on your shields you can just move natively onto the board itself instead of connecting them through the shield and through these various headers. So for the most part, I'm not going to be doing most of these headers. Once again, the purpose is to teach you how to design a custom board that's like the Arduino, to replace it for a custom design and not just to have another DIY board that you can use, because hey, you can, for what it would cost you the time to design the board and to get them manufactured, it's going to be a lot cheaper unless you're building high volumes of them. It's going to be much cheaper to just purchase the Arduino itself. There's really no purpose in doing it custom unless you're planning on producing a lot of them and you want to do this in a commercial product. So that's the focus of this tutorial, is all about teaching you how to make a design that can be mass produced for a product that can be sold. Okay, so I've kind of reviewed most of this here. Let's see what else we've got. We've got, looks like a reset line that is, so they've got this diode here. You can see it goes from the reset line up to the VN line. And normally, the only time this would ever forward bias, so this side has to be higher, is if the reset line was higher than 5 volts. And that should not be the case. That should never happen unless there's some type of like voltage overspike, ESD, that type of thing. So this diode will basically prevent the reset line from going more than a diode above the 5 volts. So it should prevent it from causing any damage. Then we just have, let me see, there's looks like a pull-up resistor here on the reset line. Then let's see if the reset, this resets only through the microcontroller programming interface, is how you'll reset this microcontroller. This microcontroller over here that runs your sketch, it does a power on reset, and you can also reset it, has just a manual switch. Okay, so I'm going to go ahead, and now that we've kind of just done a high-level overview of this ATmega USB to UART schematic, I'm going to start designing this now in our KiCad schematic. Okay, so I'm going to just zoom in here where I can see a little bit better. And we are going to I don't have everything already on this schematic, so I'm going to start with, we need a USB connector. So I'm going to just see if, I know there's one here I'm going to do a USB micro. Okay, so that will be our connector. Let's move this here. Then, and I'm going to be going back and forth between the schematic, this PDF schematic and the schematic we're working on. So pin 1, we're just going to basically, and these little TP are just test points. These allow you, just give you probe points on the board, which are always a good idea for debug that you can easily measure. It's more important if you have leadless packages. So a leadless package is a type of chip where the pins are on the bottom side and you can't actually see them or make contact to them once the part is soldered down. So you need test points, because otherwise you can't probe any of those. On packages with leads, you can just program the pin, although still the test points are nice because you don't have to worry about touching 2 adjacent pins and shorting something out and causing damage. Okay, so it's the USB power supply comes off, and it's going to go through our fuse, our PTC Fuse, which is this device right here. The symbol is a little bit different. This is not necessarily a very standardized symbol for a PTC fuse. So my symbol here, I just went with the default that's used for KiCad, so it may be a bit different. I'm going to rotate this around, and we can just route this here. Okay, we've got that. And then I'm going to put a label here. And we're going to call this USB VCC. Except I need it to be output, input. Oops. Again, USB VCC output. Okay, we've got that. Then we've got our D plus line. So we're just going to connect that to D plus on the microcontroller, the ATmega16U2. Then we got D minus connected. Then we need to make sure we have these ESD protection for each of those. I'm going to put this one on the D plus line, this one on the D minus line, and then these will both just go to ground. Okay, so we got those, the ESD protection going to ground. We do have the two resistors, the 22 ohm, that are in series with the D plus line and minus line, just to add some protection. And those are after the ESD. So basically, if there's an ESD strike, what you want is you want these ESD protection will be close to the pin, the external pin. You want all the current to go through these devices and not into here. So these little resistors can just help with that. So I'm going to go ahead and get rid of that and that. Okay. Okay, so there we go. We got let's go ahead and do a right click and do properties. You can do Shift E as well. And I'm going to go ahead and do 22 ohms. 22 ohms, okay. Okay, so that is the ESD protection for the USB. Let's see what else we have. We have our L1, which is our ferrite diode, and that actually, okay, I see I messed up. They don't not tying this to ground. These actually go through the ferrite bead first, and then that ties to ground, yes. Okay. And then we also have the shield is also tying here. And then the ground actually goes to full ground like that. Okay, so we have our ESD protection, our ferrite bead. Now we just have some capacitors we need to add for our supplies. So I'm going to just, so I've got two types of capacitors. I've got just these, this is a ceramic, so they have no polarity, no positive or negative. They can go either way. These are what we're going to be using for most of the capacitors. These are just tiny little surface mount capacitors, usually nanofarads, potentially picofarads, up to usually a few microfarads. And then for the main power coming in, the high power, high voltage, then we'll use a different type. We'll use an electrolytic capacitor, which does have polarity. So I'm going to take this here and copy it. And let's see here. Okay, we're going to move these up here. These are all, here's where, looks a little different than in the schematic that we're copying. You can see they've got power, just randomly here, here, and here, versus my symbol in KiCad has got them all the powers along the top. So I'm going to add, we've got a resist, we have a capacitor on VCC, then we have one on UCAP. Okay, VCC. So let's go ahead and tie that to VCC. And then AVCC, which is just analog voltage. So perhaps you wanted a much cleaner signal. So let's say this design, we're using linear regulators to power it, which always produce really clean output signals. I mean, there are some that are better than others, but they're much better than a switching regulator. So what you could potentially do is you may have your VCC, so the digital stuff could be powered from a switching regulator, but then your analog voltage would be powered through a much cleaner linear regulator. But in this case, we're going to tie them together, and this is going to, let's go ahead and add terminal and input, and this is going to be our 5-volt DC, which will either come from the USB or it will come from our 5-volt regulator. And then we just have the ground for that. Just that capacitor here. Okay, there's that. And this is a 100 nanofarad. And you can see here, I've already got the footprint for this capacitor, and this is sort of the main number for, is an 0603. I know it seems like a really arbitrary number, but that's the size number for surface mount passive components usually. So capacitors, resistors, inductors, and like 0402 is another common one. That's a lot. Those are really small. They get a little bit hard to handle. You drop them and you can't hardly see them. They're even smaller than that. I think it's 02, 04. That gets where those are crazy small. 06, 03 is a good size. They're still pretty small, but they're small, big enough that you can see them. So it's, unless you're really pressed for size, that's usually my favorite size. A little bit bigger would be an 05 or an 08, 05, but I wouldn't go any bigger than that for most of these components. So I'm just going to go with the 06, 03, and this is 100 nanofarad. Then next we have, so we just did this cap here, which goes to VCC and AVCC, and then you've got this 1 microfarad cap, which goes to this UCAP pin. So this is basically this microcontroller has an internal 3.3 volt regulator, and almost any regulator needs an output capacitor to keep it stable because there's a feedback loop, and without the capacitor, regulators can quickly turn into oscillators. So that's you need this cap here on this pin here. So it's a 1 microfarad, and it's on the U cap. So let me add that now. Find U cap. Here we go. So we're just gonna just copy this one, and it's a 1 microfarad. Okay. Right, and then next we have our crystal, and that's going to go right in here. So I think what I'm going to do is I need to make a little room here. So even this is going to go off the sheet, but that's okay. I'll fix it in a minute. And we're gonna do, yes, okay. I don't have a, oh, here we go. Here's a crystal. Okay, I do have that already. So we're going to rotate it. So it's going to go between here. Okay, like that. And then you have two shunt capacitors that you. And for the Arduino Uno, the crystal that they're using here actually is one that has these two capacitors built in. Most crystals, you need to add this as two separate, you need to add these shunt capacitors. It's required for the oscillator to work. This particular one that's used in the Arduino has these built in. However, that crystal is no longer available. I looked it up just on DigiKey and some different distributors, and it's marked as obsolete. So we're going to have to just use a more generic 16 megahertz crystal, and we'll pick a part number for that here soon. Right now, we're just going to focus on getting the schematic right, and we can always fine tune or adjust the part numbers. Okay, we got that. Okay, let's see what else we have now. Go back to our schematic here. There's also a 1 mega ohm resistor here across the crystal. So let's add that in. And then, of course, we have our grounds. Okay. Then the rest of these are all just the various GPIO pins, so general purpose input-output pins. You can program these to be inputs or outputs or different serial protocols, for instance, UART, and that's what we'll end up using some of these for the UART that will connect into the primary microcontroller, and then some of these will be set up for SPI for the programming interface. Okay, let's see what else we have here. I didn't put this diode here, which was on our reset line. And it actually goes to the 5 volts, so I'm just going to slide that over there. So I can just draw a nice little wire right there. Okay, so normally this is always lower than that. So this diode most of the time is just reverse bias, which means it kind of isn't really doing anything. It's only there for protection. It prevents this from ever going above the 5 volt rail. And then we'll also need to tie the reset into our programming connector once we get that on there. And then we just need, we need a pull-up resistor as well here. So a pull-up resistor that you'll hear commonly is just a resistor that's tied between whatever the main node is that you're trying to pull up, in this case the reset, and then the positive supply. And it's called a pull-up resistor because as long as there's nothing pulling this down, like say a switch, let's say that the microcontroller, if this was an output, and it was trying to put this, it would try to put this low, then that if that's not there, then this resistor will pull this net up high. So basically, if you're not pulling it down low, it's the pull-up resistor holds it up high to the positive supply. But if you force it low, then it will go low because this resistor can only pull up a certain amount because it's it's like going to be 10K, so it's a pretty good size resistance. Okay. And let's see here, we still have our programming connector. I'll add that in a bit. Got our capacitors. Okay, I think we are mostly done with the first microcontroller, so I'm going to slide this back over a bit. Just move this over here. We just sort of copies of things that we're using. Okay, so here's our USB port. Here's our first microcontroller for the USB conversion. Okay, now we are going to move over to the primary microcontroller and connect everything up to it. So it's got a few less components, support components, mainly because it does not directly interface with the USB port. So you don't have the ESD and the fuse and the ferrite bead components that you have with this USB microcontroller, which does interface with the outside world more than this one does. Although these GPIO pins obviously go to the outside world, that's typically only on a DIY maker type of project. Most of these, for any type of commercial product that would really have consumers, most of these are going to be internal pins. It's only pins that go to the external world that the customer could accidentally touch that really need the additional ESD protection. Okay, so let's go ahead and just start with the crystal. We're going to move this guy over here, this XTAL1 and XTAL2, that's where the crystal goes. And I'm just going to, what we'll do is we'll end up using the exact same setup over here. If I can select the capacitor. There we go. So let's go ahead and do that. And once again, we have that. Okay. So let me go here. Oops, I did not want to connect in there. I just wanted to make some room here. Okay, there we go. So we have our other crystal, and we'll get into this when we start to do the PCB layout. This is one of the circuits that's kind of critical in regards to how things are placed. Most of the layout on the board like this isn't really that critical. It's typically the things that require the most, that have the most complexity when it comes to designing the custom board, are anything that has really fast switching. So a clock signal, even though 16 megahertz isn't really that fast, it's still fast. So anything that's switching quickly, like a microprocessor, get data lines or anything like that that transitions quickly. Analog signals you have to be careful with, especially if they're, if they could have potential to pick up noise. And then anything with high power you need to be careful with as well. Okay, so we've got that. We got our crystal. Let's look at our power supply for this one. We have our the VCC line. Let me go to our one here. So we have our VCC goes to 100 nanofarad. Then we have AVCC goes also to 100 nanofarad to ground. But then it's also got an inductor from between the 5-volt power supply. So basically what they're doing is they're just adding some filtering to this AVCC, since that's your analog voltage power supply. So you want that to be as clean as possible. So this little inductor is just helping to make sure that this is a really super clean voltage. Okay, so we've got 100 nanofarad on both of those. I'm going to just, let's just copy, well, let me just copy this one here since it's already 100 nanofarads. And, okay, I'm going to actually rotate. Well, it doesn't matter, it flips to the text. Okay, so what we're going to do is we're going to have this one go here, this one go here, that go there. I'm going to rotate that ground. Okay, so we have the 100 nanofarad on both of those lines. Let's go back here. So VCC, that's going to go to 5 volts. And then, okay, then we have an inductor also. Okay, so this line here, let's go ahead and add in a label, 5 volt DC. And these labels are just a way of connecting terminals or nets up together without literally having to draw a wire everywhere, because it can just make it a little bit messy. So I'm going to just add this global label, 5-volt DC, and its input. And yeah, okay, like that. And let me see if I have an inductor. Do not. Let's see if I can find just a quick symbol for an inductor to add down. This. Okay. And that's going to go here. And then, so the 5 volts comes through both sides. Here it just comes 5 volts in. You have the decoupling cap, then it goes to the power supply. Here it comes through, but it goes through this 10 microhenry inductor for filtering. You've got a capacitor here, so you've got an inductor, an LC circuit filter, and that filters out any noise for the analog voltage supply. Okay, so we've got the crystal, we've got the power. Now let's do the reset line for this. So we're going to need to start with, we're going to have our pull-up resistor, then we need our capacitor, and then let me see, I think we have a diode, protection diode they have on there. And then finally we're going to have a push button switch, just a simple push button. Here, let's see not sure what happened there. Okay. Push. Okay. Okay, and we'll just put this here. Now, I'm just using a generic symbol for a push button. We'll have to eventually figure out exactly what push button. When we go to do the PCB layout, we need to know the exact size and the pad spacing and dimensions and all that good stuff. Okay, so let's go ahead and connect this up. We're going to have our reset line with a pull-up resistor, protection diode. This is going to the 5-volt supply, so I'm going to add a label by VDC input, and then we've got this capacitor here. Let's go ahead and connect that up, and that's going to go over to the first microcontroller. So let's see, whoops. So this capacitor here, it's going to go to PD7, okay? And PD7 is right here. Okay, there we go. Next, we need to tie this in. This is our, and then this side will just go to ground. Okay, so what happens is this resistor here, let's go ahead and, this is going to be a 10K resistor, if I can get it, the right thing selected, 10K ohm resistor. So this pulls it up, it keeps it from resetting, but if we want to do a manual reset, or we just push the button, that grounds the reset line, that resets it, and then we can release. And we also have this capacitor here, which goes over, so the first microcontroller can do a reset on this one. And okay, so, yep, okay, so we are good there. I'm noticing we don't have our actual chip ground yet. Okay, so there's that. Now, the main thing we need is we need to connect our serial lines. The output of this is, because this microcontroller is taking the USB, converting it to UART, and a UART is just a serial protocol, and there's two lines. There's a RXD, so receive, and then there's a transmit. And you got to So the receive of one end goes to the transmit of the other, and then the transmit of that one goes to receive of the other. So you always want to make sure that you've got receive going to transmit. So let's pull up this schematic here. Let me zoom in down here on our lines. It's these two lines here. And let's just look. So this first one here, they're calling M8. I'm not sure what the M8 is, but they're calling it, this is the RXD line, this one here. So you can see it goes here, and yeah, it's an RXD on our primary microcontroller. So generally you want to give everything in terms of the primary, the master microcontroller. So for our primary master controller, this is the receive line. So that's what they name this line, is the receive RXD. But you can see if you follow it up to this microcontroller, it actually goes to a TXD. So it goes to the transmit line, even though they're calling it the receive line. So I want to point that out because that can be a bit confusing at times. It's always best to just name things from the perspective of the primary or the master microcontroller. Okay, so we've got PD0 going to PD3. And we also need a resistor. Okay, so we got, what was it again? It was PD3. Okay, PD3 on this guy here. And I think the next one is PD4. Okay. So we're going to connect this to here. That to there. Let's just make sure it was PD. Oh, nope, I'm wrong. It's PD2. That's why you don't guess. Okay, so I'm going to get rid of that. Leave that guy there. Okay. So PD3 is this one, and it's going to go over here. PD0. Okay, and then this, let's double check. So that goes to PD0, and then the transmit goes to PD1. That. So 1K resistor, 1K resistor, and this one, let's make a little more room here, scoot that down. Okay, so this, I'm going to just call this RXD, and then this one TXD. All right, so let me just confirm this again. So the RXD goes from PD3 to PD0. RXD, PD3, PD0, and then the transmit goes from PD2 to PD1. Okay. PD2, transmit, PD1. Okay. Okay, there we go. We've got that. Now let's see what else we need here. We don't have these two LEDs, which basically are made to just flash when it's transmitting or receiving, just so you can get a visual indicator that communication is happening. So I'm going to go ahead and do that. That's PD4 and 5. So I'm just going to add, I don't have the specific part number for the LED. But right now, we're just going to use the LED symbol, and I'm going to just let's do it like this, that, and then we're going to need a resistor here, here. Okay, and then that's going to go to our 5 VDC supply to input. And we're going to bring this one down to PD4. This one goes to PD5. Okay, and then I'll give these the same names. So 5 is TX LED. That's this one here. TX LED. And then that means this one here will be RXLED. Okay. Oh, then we want to be 1K. You're not going to get much current flow if you have a mega ohm resistor. These resistors are for setting how much current goes through the diode. Okay. All right, there we go. We got the transmit, receive connected up. Okay, let's take a look at the schematic. Okay, we got the connection. We're not really bothering with, we're not doing the headers. Got the decoupling. Got the crystal. We got the reset circuit. We got the reset switch. Okay, the only thing really left is, oh, we've got a resistor here I missed. This goes on. Okay, this is part of the reset circuit so that it can reset without necessarily this one pulling it to ground. Okay, so C5, okay, so that's a 1K to ground. So let's add that in here. Okay. Okay, we've got everything except the two programming connectors, but I'm going to skip that for now, and I'm going to jump over now to some of the supplemental components that we're going to build, like the various regulators, comparators, and op amps. Since I ended up with a little more space down in the bottom left corner for the schematic, I'm going to move these various components up there. I'm going to grab that ground and see that. There we go. Okay, and keep in mind with the schematic where things are placed have no bearing really in the real world. It's we can deal with the placement issues as all part of the PCB design. Okay, so let's let's go back to the original Arduino schematic. What they have here is, well, they just have a 100 nanofarad cap on the 5 volt. Let's just add that. That's a simple one to add, but we need to, let's go ahead and add that. And I'm just going to go around PTC. Okay, so let's give this a value. It was 100 nanofarad. Okay, next up we have this comparator. So what this is doing, this is taking the VN, so this is the voltage that you can supply externally. So it can be between 6 volts and 20 volts. And what this is doing is taking that, and it's going through a resistor divider. And each of these are 10K, so that means it's going to divide it in half. So this voltage here is half of the input voltage. So, and what they're doing is making sure, so let's just say that you've got this, externally you've plugged in to VN and you've got it set to, let's just say you're using a 12 volt supply. Okay, so you're powering it by 12 volts. So that means you've got 6 volts here. And what this is this is really an op amp, but it has no feedback. So it actually acts like a comparator. And so basically a comparator is just going to swing one way or the other based on the inputs. If this positive input is higher than the negative input, then the output goes high, is positive. If the negative is greater than the positive, then the output goes low. So what happens is we've got 12 volts here, we have 6 volts here. 6 volts is definitely greater than 3.3. So the positive is higher, so the output goes positive, that goes high. Well, this is a MOSFET, and it's a P-type MOSFET. So when the gate, which is what this is tied to, when the gate is high on a PMOS, it's turned off. So, okay, so I'm going to run through it again. We got 12 volts, we got 6 volts here, that's greater than the 3.3, so the plus is high. That means this output is high. This output goes to the gate. Since the gate is high, it means this is turned off. What that means is then it's not connected. The 3.3 volt regulator and the 5-volt regulator here are not connected to the USB VCC, which is part of the USB connector. Now let's assume that you don't have this plugged in. So what happens is you got 0 volts here, while the negative is definitely higher. 3.3 is higher than 0. So that means this goes low. This going low turns on this FET. And what it does is it allows the USB 5 VCC signal to then feed the 5 volts. What you don't want is you don't want to short two supplies. You don't want you plug in the USB, it's giving 5 volts, but then you also have 5 volts from this power regulator, this linear regulator over here, where it's taking your 6 to 20 volts and stepping it down to 5. You don't want those shorted together. So you want to make sure you have this logic set up so that they're disconnected whenever there is the alternate power source. There are different ways to do this type of functionality, but for this board, I'm just going to do it the way they did it, and they chose to use a comparator. So we'll hook that up. But real quick, while we're on the this is actually the same chip. This LMV35A or 8i has 2 of these op amps. So this one, see, there's no feedback. So what's on the output does not go back to the input. So there's no feedback, and that makes it act like a comparator. This one, the output is shorted to the negative input. So this does have feedback, and specifically it has the most feedback because the output isn't divided down or attenuated and then fed back. The full output goes back to the input. And this is called a unity gain amplifier configuration. And what it does is basically whatever's on this positive terminal ends up on this output terminal. Well, then you're thinking, okay, well, what's the purpose of that? But the difference is, even though the voltage the output voltage will track the input voltage, the buffer allows it to provide more current. So for instance, they're using this to drive this particular LED from the this SCK line, which is just a clock line for the, let's see here, that's for, is it SCK? One of these over here. It's for the clock line. Here's SCK2. I'm not seeing SCK1. Oh, okay, here it is. Here it is. It's this one here. Okay. So this is just so you can kind of see when this clock, you've got a clock signal on the programming connector for the primary. And they didn't want to drive that directly from that pin and load that pin because that's a clock signal that's being used. You don't want to load that down. So this buffer basically buffers it. So whatever, this output can drive a lot more current without impacting the input here. And that's the purpose of this little circuit here. So same op amp used for totally different purposes. This is actually a digital application, and this is an analog application of it. Okay, so let's go ahead and connect those up now. Okay, so I'm going to make the resistor divider. Okay, and we're going to do 10K on this guy. 10K on this guy. And let's just get this guy out of the way. We don't need that. And then we're going to go around it. That. And then we're going to have a label for VN. It's an input. Okay, so we've got that. And let's go back here. So you've got that divided down, and that divided down goes to the positive terminal of our comparator. So we'll just type this here. Just to keep it the same. You can see these are they've got a U3, B, and A. So it's all in the same chip, but the pins are different because this chip has 2 of these. So I just want to make sure I'm using the exact same one that they're using in the schematic. So they are using actually A. Okay. So I'm going to get rid of that. Move down to there. like that. And then we're going to just, we got a 3.3 VDC input. And just do it like that. There. Okay, so we've got that. And then this is going to come out. Let's actually see. I don't think I have a PFET in here. Okay, let's see if we can quickly find a PMOS. Yep, okay. Let's see here. Okay, so you want to make sure you have it oriented the same way. This diode, it's called a backgate diode or body diode. You want to make sure that's going from the USB VCC to the 5 volts. Let me see if I can here. Yep. Okay, so you can see we got the same. We got the body diode, which is this little part here. It goes this way. Okay. So we're going to tie that there. And then I'm going to USB VCC, just to add a label here, USB VCC. And okay, then that comes out and that's going to go into U2, which is our 3.3 volt regulator. So let's go ahead and let's move this guy. It's U2 on their schematic, but it's U4 on our schematic. Okay, so I'm going to connect this here. We're going to just, this is an enable pin, so when this is high, this regulator is turned on. They just have this tied to the input, so it's always turned on. A ground connection. Okay, we're going to call that the 5 volt signal. This here. VDC. And this, yeah, I'm just going to say this is bidirectional because it could be really an input or an output. If we're using the USB VCC, then that's the 5 volt is an output. If we're not using this, then the 5 volt comes from this guy here, so this is kind of serves as an input. Okay, and then all you need is a microfarad, 1 mic cap on the output of this regulator. This pin here, this BP, we're not using. It's a bypass pin. It's would mainly be used if you're mainly concerned about ripple on the input and you don't want that to make it to the output, or you want really low noise. And I'm going to just stick with what they've chosen, and they've chosen to not add the, well, it looks like they're actually, it's called a BP pin on my schematic. They're saying it's a not connector feedback. So either way, it doesn't really matter because we're not going to use that pin. I didn't think this was a low noise regulator. Usually you only see a BP or you'll see NR for noise reduction, same thing. Usually you see that on just higher performance linear regulators. Okay, and this is now our 3.3 VDC output. Okay, back to the schematic. Okay, so we've got all this done. Got that. Okay, we don't have this guy here set up yet, so let's go ahead and do that. Okay, so we're gonna, this is where we'll connect our SCK, call it input. Then we're gonna short the negative terminal in the output. For the unit gain, make sure you always want the output connected to the negative. You don't want positive feedback. In most cases, positive feedback is a bad thing. Not always, but that's when you get things like oscillators instead of buffers or regulators. Okay, so then that, and then all we're doing is then powering another LED with a resistor. Okay, so I'm gonna actually just gonna grab one of these guys here. Connect that here. And tie that to ground. Okay, so, okay, there we go. We've got the SCK powering the LED. So we've got that done, got all this done. So now it's basically just the power connector. So they're calling it power in. It's going to go through a diode here. This just is to make sure that you can't have it power going the other direction. So you are going to lose a little bit here, a little bit of power, a diode drop here. That's probably why. Oh, well, that's 21 millimeter. Okay, so yeah, so we got to find a connector here, a barrel connector that we'll use. For now, I'm just going to start with this power in. The rest of these are just ground. So let's do a label, call this PWRN. It's an input. And then a diode, let's just do a, let me see, let me grab a Schottky, but I'm going to do a different, probably, we need to make sure that we pick the right diode. You want to make sure it can handle the load through it and reverse bias voltage and things like that. You don't want it to break down. Okay, so I'm going to get rid of the part number on this because I'm not sure yet if that's, if that's really the diode we're going to use. Probably not. And that goes there. And then that comes out and we're calling that V in. Okay, so that's V in. And here's where we have we have two of the big electrolytic capacitors, 47 microfarad on the input, 47 on the output. Okay, so let's, we're going to do this. We're going to tie, that goes there. Let's go ahead and ground it. And now we need our big capacitors. And then we also have 100 nanofarad here. And we're kind of running out of room here. I'm going to move that. Okay. Just trying to make a little more room where I can squeeze in that extra capacitor. Okay. And let's just take this little guy here. And this, and then add a label by BDC output. Okay. The next steps are I'm going to add the two programming connectors, and then we'll verify that the schematic that we'll do a verification to make sure that we haven't missed anything. Okay, so I'm going to start by adding in the programming connectors. And if you just go in KiCad, there's already a symbol for this. It's the AVR, which is the microcontroller that we're using, ISP, so in-circuit serial programmer, and it's the 6-pin. So it's just Atmel 6-pin ISP connector. We're going to select that, and I'll place one here, and then I'll place another one over here. So now we're just going to connect up the pins. We need the power supply, ground, MISO, which is master in, slave out, is a data line, and then the opposite direction is master out, slave in. So we need to connect those two up. Then we'll have our clock, and then we have the reset. Okay, so let's go ahead. Let me just start with the ground, and let's do them both. There's that. Okay, next we need to connect it to our 5-volt supply. Okay, just connect those up. Okay, now next we're going to connect up the various lines here. Let's go ahead and do the reset. That's a fairly easy one. It's just right here. So we'll do that. And then same here. We'll go ahead and just tap right here off the reset. And let's take that there. And just move over a bit. Whoops. See that you have to be careful there. See that disconnected that. I did not. That's not what I intended to do. So I'm going to try this again. Let me just clear this. All right, there we go. Okay, so those both reset lines. Now we need to connect up the data lines and the clock. Okay, so this one here is a MISO, and it's going to go to pin or BP3. And in the data sheet for this, if you looked up the BP3, you would see that it also is listed as a MISO pin. Some of the schematic symbols will show you the multiple purposes for that particular pin, but most of the time you'll need to look in the data sheet to find that. But the MISO goes to PB3, and we're going to name this MISO 2. Everything on this microcontroller is named 2 because the primary one is over here. Okay, next we're going to connect up our MOSI line, and that's going to BP2 here. And I'm going to add a label, MOSI 2, master out, slave in. Okay, there we go, we've got that. And next is our clock, and the clock goes to PB1. There. And we're going to name this SCK2, serial clock 2. Let's go ahead and just because they gave it a name, I'm going to go ahead and name this one Reset 2. Okay, so that's that programming connector. Now we'll kind of do the same thing for this one. The pins it connects to on the microcontroller are going to be different because it's a different microcontroller, but the lines are the same. It's still the MISO, and on this one, it's going to go to PB4. Okay, I'm going to name this just MISO without any number. And now we're going to do the MOSI line, and the MOSI line goes to PB3. I'm going to have to probably make some room here and get a little tight. Just name this MOSI. And then finally the clock goes to PB5. Okay, I think I can still squeeze that in here. PB5 is here. Go around. And this will just be SCK. And I'm going to name this one Reset. Okay. All right, we've got that. Let's go ahead and I'm just going to kind of clean this up a little bit. These lines look a little bit crammed in here, which, doesn't technically matter, but I'm all about whatever you can do to make the schematic more legible will always have some benefit to it. Okay, there we go. All right, I think we have everything in here now. So now what I'm going to do is, and this will be different depending on what software you're going to use, I'm going to just run an electrical rules checker. And a lot of this you'll need to set up in advance, at least in KiCad. You go under File, Schematic Setup, and you can control what type of errors are given in the electrical rules check, what's an error, what's a warning, and what's ignored. So I'm not going to focus on this too much, except I do know it's going to pick up a few errors here. So let me just run this. Okay, so let's see here. It's giving me, this first one is saying U5, pin 3. Let's just go through and check these. U5, pin 3, not driven by any output pins. And that's okay, because it's driven by this output. It's just on the other side of the diode, so the software doesn't really catch that. Not connected anywhere. Oh, power in. We're going to need a barrel connector. I forgot to add that, so we'll have to add that in. Then it's saying symbol 3 has unplaced units. And then it's also giving me an error saying it's got input pins that are not placed. So what happened here was, so this LMV 358 is 2 op amps, and it broke out each one. So there's U3A, U3B. It's got its 2 inputs and output, 2 inputs and output. But what we're missing is pin 4 and pin 8 are the power pins. And I forgot to add that part of the symbol. Most things have just one symbol for the entire chip, but certain things like op amps, if you have multiple ones on the same chip, it just makes it more convenient to break up that symbol. So what I'm going to do is I need to go back here, and I'm going to do DMV or LMV 358 type, and go down here, and it's unit C is what I forgot to add. And you can see there it is, pins 4, 8, it's just a positive and negative supply. And that's what this capacitor is for. I kind of missed that when I did the first review. If you zoom in here, you can see this 100 nanofarad on the 5 volts. This is the pin 4 and 8 that are going to this chip here. So all we need to do is, I'm just going to drag this over here. I'm just going to drag that down. And now I'll just connect that to there and that to there. Okay, now let's try to check again. Okay, yeah, that got rid of some. Let's see, we already looked at that one. We looked at that one. Let's see what this one is here. UVCC. Oh, okay. This is the power. The USB VCC needs to be connected to this. Even though they're both 5 volts, the VCC has a separate power supply from the power supply just for the USB. So what we're going to do is, this 5 volts is there even if you don't have USB, because as I've already discussed, if you don't have USB but you plug in the power through the barrel connector providing 6 to 20 volts, then this linear regulator generates the 5 volts. And we don't want this being powered if there is no USB present. So instead of connecting this to the 5 volts, we're going to connect it directly here after this fuse. So let me go ahead and just move that. And I'm just going to, there. Okay, so that's that error. Rerun. Let's see. Okay, that got rid of. Let me delete markers and try that again. Okay, now it's just saying that we're not driving this with a power output. Oops. Oh, and see, once again, how it connected there. You've got to be careful on that. I'm going to get rid of that, and I'm just going to make things simple, I'm going to just go ahead and add a input for the USB VCC. That way we don't have any chance of it shorting, but also it should get rid of that error. Okay, let's try this again. Delete all markers. Okay, let's see. U1. Okay, U1 pin 31 input driven by, okay, is this, okay, that needs to be an output, not an input. Now I need to, let's just get rid of that. We're going to have to redraw it. Yeah, actually, I'm sorry. It does actually, it is a power input on this, so I'm going to just going to ignore that warning. Whoops, wrong thing. Yeah, this is, okay, there we go. Okay, we're still getting that as an error, but we're going to ignore that because it is driven by a power pin. It just doesn't recognize it as being a power pin. So we can ignore that one. Power pin not driven by, oh, pin 3. Let's see, pin 3 and pin, oh, that's U5. Okay, that's a different one. That's this error here. We already confirmed it is driven by a power pin, but it's just the diode confuses it. So we can ignore those two errors. And then we've got this one here. And it's the same way. This one is driven by a power pin, but it's just, there's an inductor between it, so it's not recognizing it. So we can basically safely ignore all of these errors and warnings. And if you wanted to, if you really wanted to make them go away, you could go input power pin right here. I'm going to change it to ignore. But you obviously have to be careful. You don't want to ignore. Okay, so the only thing left we've got is we need a barrel connector for our power coming in, which is right here. Okay, so we just need to add our barrel plug, and I'm just going to use the standard symbol that's in KiCad, barrel jack. I'm going to put it right down here by our input supply. Whoops. Okay, so let's go ahead and connect up our ground, and then we're going to in output. Okay, there we go. I think that should be everything. Let's do one more quick check. Yep, 0 errors, 0 warnings. Okay, so there is our completed schematic. Once again, the only thing I've not added are all the various header blocks that you would want to add if you were going to use any shields with this board. But however, once again, the focus on this is designing a custom board and getting away from using the Arduino shields. So I'm not going to bother for this tutorial showing you connecting up all of those various headers that are almost entirely just connected up to GPIO pins. Okay, so now we're going to start on the PCB layout, and that's our next step. Okay, so we're ready for the PCB layout. So I'm going to open up a blank PCB editor for this project. And then I'm going to go under Tools, and I'm going to do Update PCB from the schematic. And we're going to get a lot of different errors here. These are all missing footprints. So mostly these are some of the standard symbols that I used, you know, for instance, the USB connector and the barrel connector and different connectors. I used the standard symbol that did not have the PCB footprint associated with it. So what we need to do is we need to go back into the schematic, and we're going to select footprints for any of the symbols that are missing here. So there's quite a few of them. A lot of these are, you know, the 2 programming connectors are listed twice, or the same diode is listed a few different times. So there's not quite as many as it seems. But I'm going to go back to the schematic now, and I'm going to fix all these missing footprints. Okay, so let's. I'm going to just start. Let's just start with the USB connector. So I'm going to do here. I'm going to go under footprint, and I'm going to now do USB And I wanted this micro B, I believe. Yes. Okay, so this one here, so I'm going to just double click, and now we have the footprint associated with that USB connector. So that should get rid of that error. So I'm going to, then we have our two programming connectors here. You can see there's no footprint, so I'm going to just click on this little symbol here so I can search for them. And so I need to go under connectors, pin headers. 2.54 millimeters is the pitch between each of them. So I need to go down, and we need a 3x2, or 2x3 I should say. 2x3, and we'll go and do a vertical. So the pins would just stick straight up out of the board instead of sideways. We could go either. So we'll do this one here, 2x3 surface mount. Okay, so I'm going to double click that. And we'll do the same thing over here. Okay, so there's our two programming connectors. Next, let's tackle, we have where's our little reset push button? And we're going to do a footprint here. And some of these I've already looked up. Some of them I'll show you me looking them up, but mostly some of these I've already searched for what the footprint needs to be for the part number that I can find in stock. Okay, so I'm going to go button switch. And I'm going down here. Yep. This little guy right here. Okay, that's for our switch. Okay. Next we have our inductor for our AC, this guy here. For this, I'm going to just use a standard surface mount 0603. I'm going to go under inductor, SMD, and I'm going to do this guy right here, 0603. Okay, we've got the inductor done. Now, let's do our two large electrolytic capacitors that are on the power input. So these are 47 microfarads, and the main criteria when picking the capacitor, I mean, there are different specifications, but the main two is obviously how much capacitance and the voltage that it can handle. This capacitor will never see more than 5 volts, but this one will see up to over 20 volts. You could use two different capacitors, lower voltage rating for this one, but that's kind of, that just adds complexity. If you can use two of the same, that just is one less capacitor you have to stock or find. So we're going to do both of these, and I'm going to use a 25 volt rated capacitor. So I'm going to go here. Here's the part number I had already pulled up. Capacitors, surface mount, and the capacitor we're going to use is a 6.3 by 5.8, this guy right here. Except I wanted this guy right here. The C electrolytic 6.3 by 5.8. And I had to look that up in the data sheet for this particular capacitor. Okay, so there's that one. For that one. Okay, those are the two electrolytics. Next we have our switch here. And actually, I used a generic FET, but the same one that was used in the original Arduino is this guy right here. They actually give you the part number, and you can search for that. And that's actually one of the one of the components in the library. There. So if I use that symbol instead, then I can. It already has it with it. So I need to mirror this. Oops, mirror it. Okay, so let's make sure we got these the same orientation. You can see we want this diode here, this little body diode. It's just sort of a parasitic. It's not really something that normally wants to be there, but it's part of the semiconductor device it's made. So it also includes this diode, whether you want it or not. So I'm going to get rid of that. Here, this in there in a sec. Okay, and then this one, if I just shift E, you can see it already has the right footprint associated with it. Okay, we've got that. Next, we have our various LEDs. I'm going to, for all of these, you could do different colors for these. You could do whatever you want. I'm going to, for all of these, I'm going to use the same, just an 0603 LED. I'm going to go under LED, SMD, make this right there. Okay, that's for that LED. Then we have this one here, this one here. Okay, that's the LEDs. Let's see what's. Okay, this one here, I think I went in and added this already. So this, because it comes in different packages, they didn't have a footprint associated with. This is for the chip that has the comparator and the op-amp in it. But if you go to the data sheet, you can see that it's a VSSOP, which is under package SO. There are different types of SO packages. So we're wanting the VSSOP, and it comes in two versions. There's one that is 2.3 by 2 or 3 by 3 millimeter, and I've just selected the 3 by 3 millimeter. Okay, so that's for this guy here, and then the power for it. And then we have our barrel connector here, and I'm just going to go with one that they actually have available. Let's see. Yeah, this one here. And this may be rather large. You could maybe find a smaller one if you wanted to. I'm going to just go with that. And then the only one left we have is our crystals. And these are both the same. I'm going to go here. And I think it is actually crystal category. Yes. And then we were going Abracon AM. Yes. Okay, so that. There we go. Okay. And I'm going to do it. Save. Now I'm going to go back into the PCB layout, and I'm going to do update from update PCB from schematic. Okay, the only symbol missing is Y2. That's the other crystal, and that's just because I forgot to do it for both crystals. I'm going to do this guy here. And let's do this again. Update from PCB. Update PCB. And you can see we got no errors this time. There we go. Okay. So now we have all of our components here. And now it's just a matter of placing everything and then doing the routing. Okay, so the first step is I'm going to just kind of start placing these components. Most of them aren't real critical where they're placed. I mean, some of the capacitors and the crystals need to be near the chip, the microcontroller that they're supporting, but overall most of the components don't necessarily have to be, along like the edge of the board, except for our power connector and our USB. Those are both designed so that they're going to be along an edge of the board. Okay, so I'm going to just kind of start placing I'm going to be referring back and forth to our schematic. So U1 is our main one, is our USB converter, and then U2 is the main one. Okay, so let's just start by, I'm going to just grab U1, U2, we'll put over here. Then we've got, let's go ahead and move the programming connector for that one, programming connector for this one. Then we're going to have, this is our one of our converters. This is our op amp and comparator. There's a push button for our reset. And we have our two big electrolytic capacitors. Those are going to be, let's put everything up here by this power connector. And then this is our main converter that is going to use those big capacitors. And then we also have this smaller one that converts the 5 volts down to 3.3. Okay, and let's see here. We can just kind of move this. And I'm not going to really worry about on this board. I'm not worried about the size. We're not trying to, make it the exact same size as the Arduino. It will probably end up being smaller. We don't have the headers and stuff, but I'm also not purposely trying to squeeze it down. Just that adds a lot of layout complexity and just takes more time. And, I'm kind of just wanting to stick to more the fundamentals on how to do this. Okay, we'll go ahead and move this. Let's just keep this here as well. Okay, and let's see here. Let's go and start putting the capacitors next to. Okay, so we've got the two big electrolytics go here. C16 also goes on the output. So let's take the C16. Looks like this guy here. So I'm just going to put that here for now because it's going to go on the output of the 5-volt regulator. Okay, so that's all of this. Oh, then we have D6, the Schottky protection diode. Where's D6? Those are, here's D6. And that's going to put that like up here for now. We'll have to move that all around when we start doing the layout. I'm going to get these down a little bit. Okay, so that's the power. Let's see what else we've got down here as far as the power. So we've got all of this, all this, this here. We basically got all sort of placed. Then U4 is, and we have this cap here. It looks like we are missing a capacitor on this node right here. Let me go back to the original schematic. Okay, they do not have a capacitor there. I guess they are just using this. Well, I mean, keep in mind this 5-volt supply already has, it's got this little 100 nanofarad, it's got this 100 nanofarad, and it's got this 47 microfarad, but these are only if we're powering it from the main power input, not through the USB. Let's okay, actually those would be there. Okay, so they don't have a capacitor right on the input, which normally I would probably do, but I'm going to just follow what they've got here and try to not modify it too much. Okay, so C13 is going to be on the output, and then we have Q2. So is that C13? I think that's C13, yeah, goes on the output. And then we have Q2. Where is, oh, here it is. just kind of move it right there. Okay, that's all the power. Like this, okay. R13 and R14 are going to go near U3 and 3. Okay, 12, 13, and 14. These two right there. Yep, okay, there we go. Okay, so those are going to go near U3. Okay, U3 is down here. Just kind of move those right there near it. We'll move this somewhere else. It's one of those, it just doesn't really matter at all where you're going to place that. Okay, then we have R15 and D5 also go with U3. R15 and D5. R15, where are you at? Oh, whoops, I can see I grabbed the designator for it without. Did not mean to move that away from it. Okay. I don't want it on top though. There we go. Okay. So that's R15. And then what was the diode? It was D5. This guy here. Okay, that kind of all goes together. I'm just going to place that there. Okay, we've got all this. Let's maybe move this here. Okay, so we've got, then we need C12 goes with U3. C12. I got it there. Okay. Okay, there's that. These are all sort of random. Okay, I'm going to go ahead and move this kind of near over to that microcontroller since that's part of the reset. L1 is the ferrite bead for the USB. Then we got the crystal 1 for the USB to UART converter. We got the second crystal for our primary. Our fuse, that's going to also come off of the USB connector. We got ESD 1 and 2 and C4 all go there. Okay, these two guys here are our these are going to go over. And these are the ESD, so we want to make sure we place them close to the external pin because we want those to basically absorb any current from an ESD strike before it makes its way to the actual microcontroller. Okay, R2, R3, and C4. Okay. 2, these are just the serial resistors that are part of the 2 data lines for the USB. Move those over here. And then I think it was C4, this guy right here. Okay, C4, and we'll move him over there too. Okay, let's move this down a little bit. And, okay, I'll rearrange that once we start laying out that particular circuit. Okay, so now we just mainly have these other components that we're going to place. So D1 and D2, I think, go on each of the reset lines. D1 and D2. Okay, yeah. Okay, let's put that here. And let's put that that over there for now. Okay, let's see what else we have here. We have C5 and C6. And yeah, C5, C6. Let's go ahead and place it. We still have to set the value of these. So we'll have to pull up the data sheet for the crystal, and it will tell you what these what capacitance these need to be set to. But I'm using just a standard 0603, so you don't technically have to do it because you can decide later what the capacitance will be as long as it fits in the 0603 package, which you'll be able to get any capacitor size that will fit in that package, the 0603, so 5 and 6. Okay, so these are gonna, I'm just gonna, it's not where the final go, but I'm just putting them near it. And R4 also goes there. And let's just do the same thing for the other microcontroller. R6 and then C7, 8. And I think it was R6. Yeah, 1 mega. Okay, we got that. Let's see, let's go back to this one here. Okay, R5 we need to place. That's going to go next to D1. D1. And this one we'll have also is R6. Oh, we already have that one there. Okay. So we've got this here. We've got this. We need our decoupling capacitor, so C3. Just going to put this up here near the microcontroller. And then we have C9 and 10 for the primary. Okay, I think we placed L2, I think already. Let's see what else we have. We have 8 and 9. Those are the serial resistors for the two UART lines coming from the one microcontroller that goes to the primary microcontroller. So 8 and 9. Okay, then we have R10 and R11 go with the two diodes, 3 and 4. Okay, once again, I accidentally grabbed the die designator and moved it away from it. Okay, I don't know if that one goes. That goes to R12. Okay, so I think it was, let me just make sure it's 10 and 11, and then 3 and 4 for the diodes. 11 and then 3 and 4. Okay, just kind of place those over there. And we just have a few more. Let's move that there. Okay. Now we just have these components here. Let's see. Once again, I dragged something. Yeah, I got this 10K away from the R7. L2, okay, L2 is going to go here. We'll have to probably move those around. These are going to go up here with L2. And we just have C11. Let's see where the C11 goes. Okay, C11 is part of the reset. R7 is as well, and R12. 7 or 12. Okay, these are all going to be part of the reset for the primary microcontroller. So I'm going to move those kind of like right there. Okay, there we go. So we loosely have everything placed. Now, obviously this is not going to be an optimal board dimensions like this. So probably what I'll do is, let's do something like maybe Just move this down here. And then we can have kind of a more regular board size. Obviously, our board edge will be here, so we'll need to move that. We'll have to move back any of these. So I want the board edge of this jack to align with the board edge for the for the USB micro, and we'll put that like that. So our board size will kind of be like something like that. And also I'm going to, since I'm not worried about size, I'm going to just be using 2 routing layers. It's a pretty simple design. I think we can get everything with just 2 routing layers. We may have to via back and forth a little bit, but that's okay. We've got plenty of space, and we don't really have anything that's sensitive that can't handle being, via. A via is basically just a hole with a metal in it that connects your top side trace to your bottom side. Okay, now I'm going to just start kind of connecting things up. Okay, so I'm going to start connecting things up. I'm going to just start with the power coming in, and we'll just go from there. So I'm going to move this down. Let's just zoom in here. So I need to rotate this, and we can just start connecting up. So it will highlight where the track goes. And so for most of this board, I'm just going to be using just sort of the minimum width traces. But yeah, they've got it. Track width is set at the default that I'm using is just 9.8 mils, which is going to be plenty wide enough. You can handle that's probably well over an amp of current, which is more than we should see. So we could just stick with that. But if we wanted to, especially for this this main power coming in, I could make that something wider. Let's just crank it up to 15, for instance. 10. That's as close as possible. Okay, then the VN comes through that diode, and now let's see. It's going to do 2 things. It's got to go mainly to the regulator, but then we also are going to have this capacitor here. So let's go ahead. I'm going to move this right here, and I want to put this close to the pad. So I'm going to go from like that, and then I'm going to connect that there because we want it ideally on the pin that it's connected to for the regulator. And, once again, I could go ahead and increase the width of these, but I'm just going to keep it at the 9.8 that it defaulted to. That's more than sufficient for our application. Okay, and then we have, let's go to the schematic. So this is what we're doing here. We've got the diode, we've got that. Pin 1 will go to ground, and pin 2 is our output. Oh, okay, so this is our main output. Then this is just for the heat sink. Basically, this is allows it to just dissipate more heat. Okay, so what we're going to do is I'm going to go ahead. I'm going to rotate this around. Let's get this other stuff out of the way. This, and then this. And notice how it highlights it if you start to overlap components, which you obviously don't want to do. Okay, now any of the grounds I'm not connecting up because those will be picked up at the end. We'll use what's called a copper pour that will basically just fill in any empty space with metal, and that will be connected to the copper. Okay, back to the schematic. Okay, so we've got, oops, wrong one. We've got this here, C16. Let's go ahead and connect that up real quick. And I'm just going to place it like right there. Yeah. Once again, the ground will leave unconnected. And okay, so we've got this here done. Let's go ahead and now let's do this U4, our 3.3 volt regulator. Okay, so this is where we're going to have our switch. I'm going to move it over here and get it connected, and then we can relocate it. Okay, so we've got pin 1 is going to go to our MOSFET. And I'm going to just rotate this around. And we'll connect that up, and it's going to go to U3 and then C13. It's going to go right here on our output, so I'm just going to put it as close as possible. Okay, and that's kind of all there is to that. We still have to connect up the other signals going to it, but we'll kind of do that here separately. Let's see where we want to put this. For now, I'm just going to move it back up here. U3, okay, let's go ahead and just connect up 13 and 14. 3 is here. Three. That, and then that's just the routing. Basically, I'm not doing any of the routing that connects between the different subcircuits. Right now, I'm just kind of focused on connecting up each subcircuit. C12. Okay, and that's going to go. Okay. Just a little bit over. This a little bit here. Now we can move this close as possible to the pin that we're protecting. Drop that again. Go. Okay, and then we have that one, R15 and D5. That goes to ground. And we're going to connect 6 and 7. Let's see. Oh, because they're shorted together. It's unity gain. Mainly 7 is what we're looking for. And we might as well go and short those together. For the unity gain configuration, output just shorts to the feedback. Okay, we've got that. And we have this. Okay, so we have everything here connected. Now let's maybe go ahead and start on the USB connector. Okay, it's gonna first come from, here's the power, and we're gonna, whoops, I gotta rotate that guy around. Let's just do it like that, with that little branch. Okay, and then we have our D lines, so this is where we need our ESD protection. Okay, ESD there. I'm going to get rid of the part over here just to make it a little cleaner. There's the two data lines for protection. We got this guy here. Again, I'm going to get rid of that. And let's see how that connected. I think that was the ferrite bead that's in the, okay, so the shield. Okay. The shield is going to connect all these up. And then that's also going to go to that guy right there. And then we just have our ground right here, which we'll grab with our copper port, and our ground here. Next, we just have, let's get rid of the values. And ideally for the USB data lines, you want them to be the same length and kind of just run parallel together. It's not quite as critical as it is for some other types of designs, but it's still a good idea. What I think I'm going to do is I'm going to disconnect the ESD, and we'll via for those. We'll do a via. Like that. There, these can be kept really similar. And now we just have to do it via here. Via. Actually, I'm going to not do it that way. Let's just pour out and then do. Well, this one is okay. That one you don't need a via because it's right there. This is the one that is a little bit more problematic to grab, but that's okay. And we're going to via down to the bottom side. And we're on the bottom side. Now we can just go here. That's another via. And just to sure we don't get a spacing violation, move that up a bit. Okay, so the ESCDs are connected to both. This one goes vias down to the bottom metal and then vias back up and then connects. That way, both of these, I don't want one of the data lines to have vias and the other to not. I want them to be pretty similar. Okay, what is going on with C4? Okay, we also have that guy there. Oh, C4 is, okay, not really related. That's our UCAP here for the internal regulator. Okay, let me make sure we've got this guy here connected up. Okay, that's what we already connected up. Okay, so C4 really, you can see where it connects. It's like there, it's going to be way over here. So let's just move that there. Okay, so there's our USB with ESD protection. This is our 3.3 volt regulator. Let's just kind of put that there. We've got the 5 volt regulator done. Okay, so basically we've got all of this done and then everything down here done. Okay, let's go ahead and do the crystal here. I'll look up what capacitor values are there. I'll do that in a moment. Let's rotate this. Oops. Yep, okay, so there's that. Okay, once again, you want these to be the same. And okay. And you want these traces as short as possible, so I'm going to move everything a little bit closer. Actually, let me route those and then move it closer. Okay. Yeah. Okay, so those are the same. Got this, okay. And while we're doing crystals, we might as well do the same thing on this guy. So minus Y2. Okay. Yeah, this is a mistake here. I accidentally, looks like in routing, I shorted this SCK line into the crystal. So let's go back to our original and see. So the crystal goes between 9 and 10. S clock is VP5. Okay, so these are the two extras. Oops, I'm gonna give, oops. Delete that and delete that. Okay, so that's back to the way it should be. Now I can just draw here. Okay. Now I'm going to go back here and I'm going to do, let me just do a save real quick and then I'm going to update it again. There, you can see that's now correct. It's not, that should not have been SCK. Rotate this around. And let's put it right where it's centered between the two pins. And that way each of the traces will be symmetrical. Okay, so there we have both crystals done now. Back to the schematic where we have left. Okay, so this, I think we have pretty much everything for R5 and D1. I don't think are connected yet. It's R5. Okay. Yeah, let's go ahead and connect up R5. Let's just see. Okay, so pin piece reset, and then we R5 and D1 go to reset. And which, oh, here's, okay, wait a second, that's my on, yeah, okay, that's the right one. So reset 2 here, okay. That's that. C3, we could go ahead and connect that. C3 is for pins 4 primarily and 32. But we're not using the analog, so we're going to do in 4. Okay, so we got to move which of these is C3. Okay, we just want to get this as close as we can, but we're also have this crystal here in the way, but this will be more than sufficient. I'm not sure what C4 was for. Oh, C4 is for UCAP, okay. Which was UCAP. go at here. Doesn't matter really. No point in wasting space. Okay, I think we have everything for the USB to UART microcontroller. Okay, we've got this. Now it's just a matter of our reset. Okay, our 72. So, okay, we have our reset line. Let's just, oops. Okay, there's that. Let's see what else ties into this. Okay, we got D2 and C11. None of these really matter too much about their connection. The reset line can pretty much just go anywhere. It's not high speed nor high current. And R7, I'm gonna okay, D2, C11, and R7. D2, R7, C11, and SW1. Oh, in SW1 we have, okay, R12 is going to go to the bottom of C11. And this die designator, keep in mind die designators can be underneath traces. That's not going to be a problem because these aren't etched away, but you don't want any of your die designators over any of the exposed pads because then you won't be able to see the die designator. Okay, let's probably gonna a little problem here. Okay. Let's see what else we have. We have L2, C9 and 10. Those are probably 9 and 10. Yeah, are the decoupling capacitors. So 9 goes to ABCC. C10 is going to go to pin 4. Okay. Here's the decoupling capacitor. Now, where was ABCC? It was here. And, okay. There. C9 there. Take you here. Okay. And then 8 and 9, what are R8 and 9? R8 and R9. Oh, okay, that's the 2 serial protection resistors. All right, let's see. Let's just see where they go. So let's move this one up here. Suspect they're both near each other. Yeah. Okay, still the 9.8. And you could go down to, I'm doing the 9.8 mil Y traces, but if you wanted to, you could go down to 6 or 5 mils would also work for most of these traces. I probably wouldn't do 5 mils for the main power traces, but otherwise that should be good. Okay, what do we got here? We just have 10, 11. Oh, I think these are just LEDs. Okay. Okay. And we're going to have to grab the 5-volt power supply for these. I'm going to put this over here just so I can kind of move this all together like that. And that. We just have the two. It's a little closer for it to be way out there. Okay, I knew I was going to probably do that, but I'm going to just take the long way around. Doesn't really matter for this line. It's just a LED. Pretty simple. Okay, that's it. All right, there's that. Let me zoom out. Okay, I think we have, well, we don't have the programming connectors connected up yet. I didn't mean to have all these set to display. Okay. There's not room easily to have all the part numbers. Usually you just have to have the die designators like U2 and so on. Okay. Now we can connect up our programming connectors. I'm just trying to see where they're all. Okay. Let's move this guy down here. There's that. Okay. And we have our mossy line. Let's just go. Ground we're not going to worry about. 5 volts will connect up in a minute. And then we just have closer now that we move the programming connector down there. All right, let's kind of do the same thing with this other programming connector. Just see where everything has to tie. Okay, kind of in the bottom again. Plenty of room there. Let's just do that. All right. Miso. Okay, that one we're going to have to do a via. So here, and then place another via, and then connect up. Okay, so that just comes on the top metal, vias down to the bottom metal here, vias back up to the top metal, then grabs the pad. We have our mossy line. And we're going to have to do a similar thing. Okay. And connect up the reset line. And I'm not gonna, like I said, this could definitely have some placement redone just to make a little more board space. Like this programming connector, I could move that and make it tighter, but that's okay. We're not gonna mess with that because that's not really the goal here. Okay, I think we have most of the things, the sub-circuits connected. Now we need to kind of start connecting up some of the, between the sub-circuits. Okay, now we're going to start connecting some of the lines that connect between the various sub-circuits. For instance, let's start with, we need these two data lines here for our USB. And I don't have, I've got this microcontroller kind of over here. I may want to switch it and move it over here. Actually, I think I'm going to do that. So let's just grab this, and we're going to move that over here, and I'll grab that, and let's move that over here. And yeah, I mean, it makes the board a little bit. Let's see if we can actually. Yeah, I'm just gonna leave it where it was. We can, if we need to, if we didn't want the board to be that wide, we could scoot this up and tighten it up. But like I said, it's not really important, so we're not gonna worry about maximizing our board size. Okay, so let's see where these two traces go. And I knew it was going to do that. And normally, like I said, you want the USB lines to be the same. This one is a bit different because it does have a via that goes down to the bottom layer just to cross over it there. But I'm not going to worry about it. I don't think it's not going to really make that much of a difference. They're still pretty similar. The main thing is you just would not want one of these routed all along the outside of the board and having one really short. Okay, so we've got the data lines connected up. Let's see, what's D5? That was just, oh, okay, that's to drive the just the LED. Let's see what we have connected that we have to connect up there. Okay, so and we just have mainly our SCK. We also have 3.3. Okay, so the SCK, so pin 5, let's this here, and where do we need to go? Once again, I'm not going to worry about size, so I'm just going to route along the edge here, and what would be normally best is if we, would have gone a shorter route, done some vias to get a shorter route than going on the outside, but not a big deal here. Main thing is I've got to access this pin, it's kind of boxed in a little bit. So we're going to have to do a via here and connect that. Okay, so there's our SCK line. That's here. We have USB VCC. That's separate 3.3 volt. Okay. Let's see. We got to get. What I'm going to do, that's a power, so I'm going to do the 3.3 volt. Well, there's really nothing else that goes to 3.3. Yeah, so I might as well go ahead and do that now. So I'm going to place a via. Okay, so there's our 3.3. This was not really for power. This is only, this 3.3 is only for our comparator. So there's no current that really flows through that. It's just this right here that goes into the input of the comparator. Okay, what else do we have here? We've got, let's use our Q2. Let's go ahead and connect that guy up. Okay, where did Q2 go? Oh, here is Q2. And that. And it's not really necessary, but you could, if you wanted to, you could make these a little bit wider of a trace, just because that is a power. So that's the USB that goes into this diode, and then it comes out, or I'm sorry, through this FET, and it goes here. Let's go ahead and just, whoops. I'll go ahead and make this 15 as well, just for consistency. And then this is the gate for it, which will come out of one of our comparators down here in the bottom corner. Let's see, I'm gonna go here. So I just do a via there. And okay, there's our gate. The gate is just this here. This is what controls this FET, whether it's turned on or turned off. Okay, we've got all this. We've got those routed, the USB lines. And okay, we've got the connectors already connected up, or the programming connectors are already connected up. Reset. Okay, we've got our transmit and receive. I'm not sure if I've connected those up yet. Let's see, that was R8 and 9 that came through. Where did those? Oh, right up here is 8 and 9. Okay, so we have not connected these. So let's see where that has to route. Okay, that's got a route way down there. So let's just go here. We're going to have to show it. Okay, there. And we're trying to get down to there. So I'm going to have to via again. And then via again. Okay, so then back to the bottom layer. I'm gonna go along the perimeter here. This would be it. There, connected there. Okay, there's that line. Now, probably will be something similar for this other one. This one, I'm gonna actually go a different route. Okay, there's that. All right, let's see here. We've got those. Okay, that's what we just connected. We need also C11. This bottom is going to go over to the first microcontroller. That's for our reset. Let's see, C11. And that's going to go over to here, okay? So I'm going to have to jump down to the other side of the board. All right, there we go. We are getting close, I think. Okay, I think that's all the lines I see right now. Do I have these connected up, D3 and D4? Where did those go? Those are on the 1. Oh, okay, here they are. Okay, yeah, we already connected those up. Okay, I think we're down to mainly just connecting up the power. So we've got 5 volts going to a bunch of different things, and then the ground will pick up with copper pores. And one thing you would do if you were doing multiple layer boards, then you would probably have like one of the inner layers would potentially be a power copper port just for doing the 5 volts, for instance, since that's the main power that we have to route around. But for this, we're just doing the 2-layer board, so we're just going to have to connect up each one manually. Okay, so I'm gonna just start with we got the programming connectors. So this guy here, and let's see what all we have to connect to this. Okay, need to grab a bunch of different stuff. Okay, I'm going to go ahead and starters. I'm going to come up here and this will be it here to here. So like that. Oops. And once again, I can be rather lax about this because nothing is high power at all. Okay, so that's we got 5 volts to our 2 programming connectors. We need 5 volts coming to each of our microcontrollers. Let's see, here we got, this needs to connect. And we got this needs to tie in there. Okay, that's our L2, we got that. Then we have our, here we need 5 volts also. We're going to grab that. We could, let's place it via, and I'm just going to tap off of that right there. Let's see what else we've got. This guy here needs to connect. I'm going to just connect those underneath the pad. And then just looking to see how best to route this. We need to get it up here. Oops, let me not do it that way. So I'm going to go here via, okay, there's that. Okay, we got 5 volts there. Those have 5 volts. That's good. 5 volts. That's got 5 volts. All right. I think that is most of the 5 volt ones. Okay, and then we have this V in. This is just for the resistor divider that is sampling the input voltage for the comparator. So this doesn't need to be anything critical on that at all. Okay, back to the schematic. We already connected that up. Okay, we do have our 3.3 we already connected. Okay, I think we are getting close enough that we can run some verification to find out what we've not connected up. We're going to have a lot of grounds that we've not connected up, of course. Get to those. Oh, here's a 5 volt there. Okay, well, that's nice and easy. I'm not sure if on U2 did we 5 volts. Oh, okay, yeah, we connected that up. Okay, I'm gonna do a verification. We still need to put down our copper pour and our board edge. Okay, before I do the copper pours and place down the board edge, one thing I did here I can't do is I routed this past the edge of the board, so we're going to have to redo that. Let's just, I'm going to route here, let's place it via And we can do, end up place another via here and a route on the bottom layer, like that. There. And that got rid of that outer trace. Okay, so there we go. Now, what we're going to do is we're going to draw the edge of the board. So I'm going to go under and select edge cuts as my layer, place a rectangle, and we're going to draw up from, go up a little bit, like that. And then the next step is we're going to place what is called a filled zone. This is for our copper. I'm going to go in here and just kind of, don't want it right at the edge of the board. It needs to be in a bit. It's wanting to know what layers I want to do. Oh, let me go back up here and go back to our routing layers. There we go. Now place a field zone. I'll just click on the first point. Then it's going to ask me what net this is going to. We're going to ground. I want this on both the top and the bottom. None of that matters. I've got the clearance and the minimum width. I just kind of set those low at 6 mils. That way the copper can go into small spaces and make sure to grab the ground. Pad connections is probably set to thermal reliefs, but just for this, that's too advanced of a topic. We're going to just do solid and a solid fill. And I'm going to do OK. Now we can finish drawing the rest of our copper pour. Kind of doing it approximate. Like that. Okay, and now I'm going to do zones. Fill all zones. And let's make sure that this looks correct. I'm going to zoom in on one of our programming connectors. You can see, so the red is this is our copper pour. You can see the red doesn't touch any of these other pads because they're not ground, but it is going up and touching this ground. Same here on this this diode. It's grabbing the ground here, but see how it's etched around the other. So that's how the copper pour works. So these, and okay, and I'm going to zoom out. Now the other thing we want to do is we want to just add a bunch of ground vias because we want to make sure that all these different ground planes, the top and the bottom, are connected, but even also some of the little ground pours may be isolated, so we need to make sure that they get connected. I'm going to zoom in on this. I'm going to just select this guy here, make sure he's tied to ground. He is, and then that way I can just copy and paste it. And for this, I'm just kind of placing them all over the place just to make sure we get good ground connection. Okay, I think that looks like a good start. So the next step is we're going to start running verification to see what we've missed, what design errors we have, and there's probably going to be quite a few grounds that we maybe have missed that we need to go back and make sure that we grab those. So for verifying that the board is correct, we're going to go under Inspect. So verifying that the board is correct, we're going to go under Inspect. So verifying that the board is correct, we're going to go in the PCB router, we're going to go under Inspect, Design Rules Checker, and then we want to make sure that we also have a test for parity between PCB and schematic. I'm going to refill all of the zones, so all the copper pours before running DRC, and let me delete markers and run that. Okay, so we're getting 2 10 errors and 6 warnings. This violation here has to do is saying that there's board has a malformed outline, but it seems to be triggered from this power connector, which has a board edge line along it that is giving this error. So this is, I'm just going to ignore this. This is not anything to really be concerned about. And the main part that we need to focus on are these missing connections. Okay, so this is, most of these have to do with the 5-volt supply not being connected everywhere. So I'm going to just click here. One thing I'm going to do is I'm going to go in and I'm going to unfill the zones. And that way I can see a little bit better and for routing and such. Okay. So let's see. It's saying 5 volts here is not connect. Oh, because I'm on the bottom layer here and there's no via, so I need to add a via, and then we'll route that connected in metal 1. Okay, so there's that one. Then what do we have here? U4. Okay, so this 5 volts here doesn't get connected to anything. And then you can also see, I think there was another, yeah, okay, so U4, 5 volts. Yeah, all I'm doing is connecting together. Wait a minute, the 5 volts coming out of Q2. Oh, okay, here's the problem. This U3 pin, or this pin 3 for U4, which is, if I had to guess, is probably an enable pin. Yeah, on off. So we need to just, we need to tie that high. What I'm going to do is I'm going to go underneath the part like that. And then we've got this diode here, needs to go to the 5 volt supply. Yeah, let's just connect this here. And oops, right here, so we got those all connected there, but we still need to tie that to our main 5 volt output, which is, okay, which is U5. Okay, so we're going to, I'm gonna go here, I'm gonna place a via, and then just go right up and tap into that via that's already there. Okay, and then we got this guy here. Let's see, whoops. Oh, okay, that was for that guy there. We already fixed that. Oh, then we got this one here is not tied. That's that one, and this one here. Okay, these are tied together, but they don't tie in. Okay, so we're going to, okay, we're gonna have to via, and then via. Okay, so that grabbed those two. Then let's see what this one is here. This is for the, okay, so pin 31, this guy, I did not connect up the USB power to our microcontroller. So let's see, where can we grab? Just close this. Okay, so we got to get up to there. Yeah, let's just go here. I'm going to go place a via, and I'm going to go in here. That's not good. Try this again. Okay, so via here. Let's see if I can make a little more space for us here. If we can get a via in there. Let's see if we can scoop this a little bit this way. There we go. Okay. So, about 2. It's giving me a problem because it thinks this via is connected to something else. So I'm going to have to manually tell it is connected to USB VCC. And now I can connect that and place another via, right? Let's just copy this via where we know it's already connected. Okay. That was for this one here. And then surprisingly, we don't have more missing ground connections. I'm a little surprised because they can be, some of them are problematic. So let's go ahead and rerun the inspection now that we've got everything cleared up, or at least most of it. Okay, we still have some missing. We have 2 5 volts not connected and 2 grounds not connected. So I'm going to go and I'm going to turn off the ground planes. Now go back under here, go unconnected, and let's see where we're at. Oh, it's just this little piece here. So one thing I forgot to do that can be a good idea is to go up and run this clean tracks and vias, and it will just basically get rid of any little pieces that don't do anything, like yeah, let's go ahead and refill those. And now let's rerun. Oh, yep, okay, so now we're down to just 3. Let's see here. Okay, looks like R11, turn off copper pores again. Okay, what seems to be the problem is this 5 volts doesn't connect into, so I've got several things connected to 5 volts, but it doesn't tie in with the 5 volts for the other stuff. So I'm just going to draw basically a line and connect this line to this line over here. And I'm going to do it on the bottom layer. So I can just cross over with a via here and then place a via there. Okay, that I think should have gotten rid of that error. Let's see here. We're going to delete markers, run DRC. Yeah, we're down to 3 errors now, or 2 errors, not counting the one we're ignoring. And these are all missing ground connections. So for these missing ground connections, what I typically find works best, especially when you're down to the last few, especially for KiCad, I don't really find this very helpful. So what I like to do is just kind of scan, go through component by component and see if there's any grounds that aren't connecting up. See, like this guy here ties into this big ground plane, so you can see it's got via, so we know that's not it. A lot of times it tends to be the chips with higher pin counts that you can't get a ground connection out. And here are the 2 problems. You can see this ground pin here. Well, the copper pore tried to make a little copper pore here, but it doesn't go anywhere. Same with this here. This little copper pore here grabs this ground pin and grabs all underneath the part, but it doesn't connect in with the other vias. So what we need to do is we need to add a couple ground vias. So I'm just going to copy that one. I'm going to put one right here. And I'm going to put another one. Let's just go ahead and do a couple right there. Okay, now I'm going to rerun, delete all markers, run DRC. Okay, so we just have that one board edge issue with the connector, but that's not really anything, and we can just ignore that. And that got rid of all of our unconnected items. There are no schematic issues, meaning our PCB layout matches our schematic. And these are all just a minor ignored test. Okay, so there we go. We have a finished and completed PCB design for your own custom Arduino Uno. Although once again, this is not something you're going to want to manufacture and use for projects with shields or anything like that. This is all a learning exercise so that you can design your own custom Arduino on your own custom PCB, along with what other functions that you need you would implement. Any of the shields, whatever functionality those provide, you would want to add to this same board design. Now, if you enjoyed this video, be sure to check out this video here where I show you step by step how to design a custom PCB that uses a wireless Bluetooth microcontroller.